Okay, I think we should start 7:10 now. So with a great pleasure, let me introduce Dmitrii Zhelezov, my colleague and co-author, who did a really great progress in the sum product phenomenon concerning subsets of Z with small product set. It's a huge progress. So please welcome. Let's start.
Thanks a lot for the introduction, and thanks a lot for having me for such a nice conference. I'm Dmitrii Zhelezov at ReCam Links. I'm going to talk about sets inducing large additive doubling today and the applications for the sum product phenomenon. So we start with like a very basic setup. So we're going to deal with multi-dimensional additive set in ZD. So D is some dimension, which is not really specified, but it's assumed to be large. And we take the standard thing in additive combinatorics, the sum set, which is like the set of all sums, and the key object that one is interested in is the doubling, which is the size of the sum set relative to the size of the set itself. And it turns out that, like in many applications, one would be interested in like finding what are like if this additive doubling is large, what are the inherent properties of this set? So maybe like there is like a very specific subset, so that like in this case U, so that like if any set contains this set U, then the additive doubling is large. So this is kind of like a witness that anything containing a set has very large doubling. And this is like what we are going to study, like in what follows. And the outline for the talk is the Fremanlemma that many of you may have heard. We are going to then go on is to figure out like which sets do induce large doubling. So which sets force all the subsets that contain it have large doubling, and then we go on with the applications to some sort of a version of the Fremanlemma with logarithmic bounds and the applications for the sum product. So if we look for the Freman theorem, it's not the hard one, but it's sometimes called the Fremanlemma. It says that if a set A is properly m-dimensional, which means that it cannot be contained in a affine subspace of lower dimension, then it has at least m+1 times A large sum set modulo some error factor. So if we want to rephrase this in terms of the induced doubling, that basically means that if one can find a non-degeneral m-dimensional simplex within a set, then the additive doubling is at least m+1 modulo the error factor. So we already can relate the induced doubling with the dimensionality of a set, and like give or take, this is like more or less the dimensionality of the simplex, but figuring out a sharp bound for the simplex, it turned out to be surprisingly messy. And one of the kind of interesting points here is that it turns out that one can instead look at a related property that we call beta in a joint paper with Matolchi, Ruja, and Shakan, which is like this device. So you take infimum over all sets A and B and look at the triple sum scaled with the square root of the products of the sizes. And this is indeed like a more general construction, and one can easily bound alpha, which is the induced doubling by Plunike-Ruja. And the key property of beta is that it actually tensorizes. So you can relate beta of a set by looking at the at projections of this set with respect to multiple slices that we're going to look in what follows. So the tensorization in a strict sense looks as follows. So assume that you have a set which is a subset of a Cartesian product. And you can write down it as a disjoint union of the slices with respect to the first coordinate, which lives in V. And then you can bound this beta by the betas of each of the slices here. And this already gives non-trivial bound, actually the best possible one can get for d-dimensional cube, because it suffices to prove that beta for a 2-point set equals to 2, and then recursively apply the theorem, increasing the dimension one at a time, and then you'll get that the size, the times that you apply this equals to the dimension, and then that the beta is the same as the size of the set. And if we look at the definition here, then it is clear that beta is at most the size of U, right? Because we can always take singleton sets here, so that the sum set in the denominator is the size of U, and the denominator is just 1. So then this infimum cannot be larger than the size of the set U itself, right? So already this kind of simple standardization property gives you the best possible estimate for a certain set, for a certain like class of sets, which is like a two-dimensional cube. In fact, like one can have a lot more mileage here, because not only it applies for the hypercubes, but also like for more general sets, which we're gonna call quasicubes. And in order to define it, like we should consider like the very general notion of fibering. So you can it's something that we already discussed. So then we have projections on a subset V, and for each projection and which coordinate, we have a slice ux and uy and up to uz for each of the like first coordinate of your set. So if we look at a triple sum, and we look at the disjoint unions of the slices, it is clear that we can independently look at what happens in the first coordinate here on the v direction, and these slices are going to be just a union of all the sum sets with respect to these slices. So we can actually look at each slice separately. And then we can bound the size of the union just by the size of the maximal triple sum on each slice. So and then we can iterate and bound the triple sum with beta on a lower dimensional slice UK. And that's how we can iterate and move down the dimension of each slice. Which actually suggests that we can generalize the hypercube situation to what we call the quasicube. The quasicube is basically the same as a hypercube, but each time the slices are just like two-dimensional two-point sets, right? So you can define it in recursive way. So any two-point set is a one-dimensional quasicube, and a d-dimensional quasicube is this joint union of exactly two slices, such that each slice is a d-dimensional quasicube. So if we get back to this picture, then we have only x and y here, and x and uy here are d-dimensional quasicube. So this is like a fairly general construction, because for a quasicube, we have like a very rigid structure, because we have only d coordinates, and it has only it's just like d-dimensional, so we can have just d projections on d coordinates. But in here, we can sort of deform it in an arbitrary way, and we have a whole class of subsets. So here again, how it looks like, we have just two slices, say with 0 with respect to like 0 and 1 coordinate, and the slices u0 and u1 in turn are d-1 quasicubes, and each slice and then goes to d-2 dimension, and so on. So each point can be decoded as a binary string. Okay, so now if we come back to the estimation of the triple sum, then the maximum is going to be taken over just like two slices. And we can have a sum over maxima, which include only betas of two slices, u0 and u1 here. And it turns out that we can actually bound quite effectively this sum over maxima using what we call weighted Precocity inequality, which is actually the central result of the paper, which says that this sum over maxima is actually greater than the sum of betas here. So that for any a and b, you can bound this sum with beta u0 plus beta u1 times the square root of the product set. Then let's give a bit more context on like why it is called discrete Precocity inequality here. So first of all, one can define what is called max convolution here for two functions. It is similar to the standard notion of convolution, but instead of taking L1 norm, which is the integral over all y, we take L infinity norm, so that you take the supremum over all possible products, such that the argument sum up to x. So f max convolution g of x is supremum over y x minus y times g on y. And in a continuous setting, it's actually a classical result of Precocity that the L1 norm of max convolution can be bounded by two norms of functions f and g. And the discrete version says that we can replace the integral here over with a sum, and here we have only 2 points here, which contribute to the max convolution. And so in the discrete version, we will have a sum over all integers, and in each point we have the value over n minus 1 and n, like 2 consecutive points, and we can bound this again with the 2 norms of 2 functions. So how does that work? In our setting, if we like go to the sum, we are actually exactly in a situation where we want to estimate max convolution, but with different weights here, like b on u0 and b on u1. And in fact, this is the same as estimating a weighted have an arbitrary lambda here. And like the question is like to prove that for any lambda from 0 to 1, we have such an inequality. And then if we have this, then we can estimate quite easily this sum over z here, because this is nothing else than the weighted max convolution. Because we can set lambda to be beta u0 over b01 plus b0, and plug it in here, so that we get that a plus b plus u, which is at least this thing, at least left hand side, can be bounded by the product of two L2 norms. Yeah, maybe like I can answer like some intermediary questions if there are any here, because I guess it might be hard to grasp like on the fly what's going on.
Dmitrii, is it true that say lambda equals 1 for simplicity, equals 1/2 for simplicity? Is it true that this, first of all, this 1/2 is crucial for you, right? And this 1/2 comes from basically Cauchy-Devine port, because in Cauchy-Devine port we have 2, right?
Actually, I think 2 here is important because we have just like 2 points to start with. So 2 here is not really this 2, but rather than the fact that we have a maximum over 2 things here. So in particular, yeah, this like if we have 1/2 and 1/2 here, this actually just makes it much easier to prove. But this is actually true for any lambda. So and that's kind of the whole point here, because like for 1, 2, and 1, 2, we can use it. We can prove it by hands, like with just some arithmetic. But if we allow this to be unequal, and this is what actually important here, because like the betas on the slices can be of different values, then it becomes harder. And this is like the main the kind of meat here is that no matter how disbalanced these slices are, you still get a very good bound, like basically the best you can. So we kind of improve on the, like, generalize on the classical result, because the classical result here is with 2, which sort of translates to the equal weights here, to something that we call weighted. And for weighted, yeah, there is no difference whether it is like very unbalanced or unbalanced.
Yeah, but I'm trying to say that this inequality somehow feels the addition. It's more general than Minkowski theorem about addition. So it's a additive combinatorial effect rather than functional, I would say. No.
Actually, this kind of thing is purely functional, because like we don't really use any additive combinatorics here, but we do it when we bootstrap it to higher dimension. So if you want to prove that beta over 2 point set is equal to 2, then you would need Cauchy Davenport for it. But this particular inequality is like a general functional analytic effect. So it's nothing than like the proof is like fairly kind of intuitive, but still like not very easy to come by, because you have to minimize like a certain functional, and you do induction on the size of the support, but it doesn't really require any particular additive combinatorial stuff. It's more like combinatorial analysis, I would say.
Okay, thank you.
And yeah, following it up, the corollary of this inequality is that beta on u is equal to u, and this is something related to what I was just talking about. This inequality allows one to do induction on these on the slices. So in particular, we get this, but in order to prove the base case, one can actually use some additive combinatorial trickery just to prove like seemingly simple fact that beta over 2 point set is equal to 2. Actually, it kind of may seem trivial, but once you go to the definition, you would like need to prove that if you add a 2 point set with arbitrary 2 sets, it's actually like grows quite a bit. So it's not like super hard theorem to prove, but it's not a trivial either. So here you indeed would need to apply Cauchy Davenport and something more. So because Cauchy Davenport will give you a bound of 1, and in order to get 2 here, you would need to work a bit extra. But then once you have beta for a 2 point set, you just like do induction, and you can go and you gain a factor of 2 every time you go to each of the slices, and that means that for a Quasicube, and actually like for any subset of a Quasicube, you would get beta as large as it can get. And again, this is like kind of the beauty here, because here B like 0, BU0 and BU1 can be very unbalanced. So like in all the previous applications of this kind of slicing technique, it was important to regularize the slices so that you have them either of equal size or of equal doubling, but in here they can be like very unbalanced, and you still have a contribution that adds up to the size of the set. So that's why you can actually prove that beta is maximal, not only for quasicubes, but for any subset of a quasicube, which is actually a much larger family, because like in the applications, you rarely have like a full Quasicube, but normally you have some like a remnant of it. And like a for the doubling, which is just square root of beta. So we got like a fairly strong result that you take an arbitrary subset of a Quasicube, and you know that it gives you a very large induced doubling. So any set containing it actually has a large doubling. And here we use this fact in order to attack the called polynomial. So it's still very important, and I mean, polynomial is small additive doubling. And the conjecture, which is called weak polynomial Fremanlemma conjecture, says that actually, if a plus a is less than ka, then a large portion of a can be contained in an affine subset of dimension logarithmic in k. This is sort of a logarithmic improvement over the Fremanlemma that we discussed in the beginning, which gives you basically dimension equal to k. But here, this is like gives you like a much more precise information that actually the sets with there is nothing. So the sets must be very low dimensional if they do not grow with respect to addition. And once we have this beta and actually alpha in our arsenal, we have like a new line of attack and in general to think about sets with small doubling, because once the doubling is small, that means that they cannot contain any subsets with large induced doubling. So they cannot contain any subsets with induced doubling bigger than k, because like otherwise a plus a would have been much bigger. So and in particular, all the subset of a must have quite small beta, less than k squared. And like going contrapositive, it says that a is free of subsets with large beta. But now we already know like a whole family of subsets which have quite large beta. So like we just conclude that if we have a plus a less than ka, then a is free of large quasi-cubes. And since this is like a fairly big family, like a fairly large family, we end up in a situation of figuring out like what actually can we say about set if it doesn't really have any large quasi-cube as a subset. And it turns out that you can have a description. And this is like, that was like a joint paper with Dmitrii Zhelezov and myself, that if you have a like a multi-dimensional set free of quasi-cube subsets of size k, which basically the same as saying that a plus a is less than k, then there is a huge subset of a which is of low coordinate query complexity, of logarithmic. I will explain shortly what is coordinate query complexity, but I just want to mention that this is strictly weaker than the weak polynomial Fremanlemma, that somehow like follows this fact that if your set has very small doubling, that it should be like not very random, so to speak. So it should contain very, it can be encoded using logarithmic number of bits, so to speak. So what is a coordinate query complexity? So assume that you pick an element from your multidimensional set, and the query complexity is the minimal number of questions, like minimal number of coordinate probes that are needed in order to figure out what was the element that you picked out of it. So in particular, for example, the algorithm would be like, look at the third coordinate, basically look at the projection of the third coordinate. If it's 2, then ask about the 6, the projection on the 6th coordinate, and then based on the answer, look at the what the last coordinate, which is 7. And once you have opened 2, 5, and 7, we kind of guess the whole word. But if, for example, the answer for the third query was different, like 4, you are allowed to choose another coordinate, and your choice of which squares to open may depend on the previous history. So this is like a key difference from dimensionality of a set, because if you knew that your set is contained in an affine subspace of dimension 3, then you can just fix 3 coordinates such that the projections of these 3 coordinates is injective. So you just always pick the same 3 coordinates, and you can figure out the element once you know like who they are. But in here we have a lot more flexibility on constructing our queries, because we can the answers the questions may depend on the previous history. So still somehow it feels like a generalization of the affine dimension. I would also stop here just to let people ask questions if there are any, because I think this is like a quite non-standard construction, and hopefully people will figure out what it is. And if not, I will move on. All right, so seems like there are no questions here. The theorem that we proved says that once you are free of large quasi-cubes, there is always like an algorithm to figure out any element in your set with a logarithmic number of queries. Basically, it says that like the only abstraction to have a large query complexity is to having like a sort of quasi-cube-like structure, in which case you would need to do as many queries as the dimension of it. So in particular, if your like query complexity is low, then there cannot be subsets with large dimension. So which actually begs a question, like what are other sets with large beta? Because like if we can prove estimates for beta for not only for subsets of quasi-cubes, but perhaps for a larger family of sets, then we can actually extend our arsenal and look at the sets which do not have even more subsets. So the set of prohibited subsets is bigger, and then we can actually gain more information about sets with small doubling. And this is, I think, our key conjecture here, is that beta actually depends only on the dimensions of all the possible slices of your set. So in particular, you can freely move your points, and as long as the affine dimension of any subset remains fixed, the beta cannot really change. And if we can prove this conjecture, that would actually mean that the family of sets with large beta is much larger, because not only we have quasi-cubes and all subsets thereof, but we are actually allowed to deform it in an arbitrary way. And basically, the only way to reduce the value of beta is to make it lower dimensional. And just to like pique your interest here, I suggest you to look at this like very simple question, like seemingly that assume that you have only like a 4-point set. You have 0, 0, 0, 1, 1, 0, and 2, 1. Can you prove that beta of this 4 points set is equal to 4, which is the maximal value it can have? Note that if we replace the last point here with 1, 1, that's going to be just a cube. And for cubes, we know that it must be equal to 4. But since this 2.1, like it's similarly like random force point, can it actually make this beta smaller? Kind of, it's very intuitive to like guess that it does not, but it turns out to be like even the two-dimensional case, it's not really clear how to have a proof of this fact. And it seems that like maybe like it is possible to prove it by hand with some trickery, but when you, for example, go to 3 dimensions, it becomes complete mess if you just try to analyze how this iterates on the slice level. So probably we here probably would need to figure out even a more general device than beta, which allow to induct on dimensions in a more efficient way. So if we can summarize what happened with beta, like is that instead of looking at the induced doubling, which is alpha, we basically came up with a device which behaves very well with respect to tensorization. So we can actually move down on the dimension. But it turns out that it's not very effective once you have points in a very general position, because then the slices are immediately just one-dimensional, and there is just like a lot of fibers which contain just a single element, and there is nothing you can do here. So it seems that we probably need to come up with even more general device so that this iteration can be more efficient. Okay, actually, this is the last slide that I prepared for this, because I was actually thinking that it's going to be like just a 45 minutes talk. But let's then go to the question session, and yeah, I can maybe clarify if there is like anything unclear here on the slides.
Dmitrii, can I ask you a question? Maybe it's a stupid one. So you have proved the theorem about a kind of polynomial Fremanlemma conjecture with complexity, this query complexity. Have you considered another families of additively rich sets, like, I don't know, not sets with small doubling, but with small Wiener norm or something like that?
Yeah, it's an interesting question, I think. No, we didn't, but I think in general, it's kind of a general technique to look at the inherent properties, so that like assume that you know that your set contains a set of a specific family. Can you prove that an for example, the Wiener norm is large. So you kind of have a witness of just by looking, but knowing that the fact that you have like a subset, then can you say something about the whole set? And the motivation here is that like this induced thing is very stable with respect to throwing out some portion of the elements, right? Because you can easily add or remove arbitrary number of elements, and as long as your subset remains in there, you still have this very stable property of like having this witness. And this turned out to be like very crucial in applications.
Okay, we can continue, I think.
Actually, that was the last slide.
The last slide. Sorry,
yeah,
sorry. I
so, yeah, I want to ask the question, and I would really interested if anyone can come up. I believe that there should be like a simple solution to this, because it doesn't seem like something that you cannot like attack. So I can probably repeat this question again. So you have a 4-point set. It's just like 4 points in arbitrary, in general position. Because you can, like, using linear transformation, you can basically reduce anything to 0, 0, 0, 1, 1, 0, and 2.2 to 1. So can you prove that this beta here is equal to 4? And let me just remind what is beta. So beta is this construction, right? So you take arbitrary sets A and B, and you just need to prove that A plus B plus this 4-point set is at least as large as 4 times the square root of the sizes A and B. Yeah, so for a 2-point set, this is kind of not trivial, but simple. And for 4-point set, this is surprisingly hard to do.
Do you have any intuition why exactly this beta works?
This beta works actually because it tensorizes. Because you have A and B arbitrary here. So if you look at the alpha, which is just like an inherent property of your set, then you cannot really say anything about alpha if you know alpha about the fibers, right? But here beta is constructed in such a way that A and B are arbitrary, and it turns out that it really helps to get to induct. So basically, this is like the situation where like proving something more general helps you with the induction, and induction becomes much easier to do. So that's why I expect that if you consider something even more general here, so maybe like not infimum, not only on A and B, but also, I don't know, maybe some transformations applied to A and B or something like this, then you can actually prove even more general result with the same technique of tensorization. Yeah, so basically the tensorization property is like this. Have anything similar for alpha.
Thank you. Thank you. So let's thank Dmitrii. And are there any questions?
Yeah, thanks a lot for having me. And I really hope that someone actually comes up with some ideas how to attack it, because I think that if we can crack this particular question, then we can prove the weak, the few products, many sums for real numbers, which I think would be nice.
Thank you. Thank you. Thank you, Dmitrii.
Thank you very much for having me.
Thank you.
Thank you very much.